All right, good morning. Let's see, just want to make sure that everything is showing up like it should be. Let's see. Yeah. All right, for what we'll be looking into today, there will be quite a few elements that will have a bit of a ring of familiarity. Again, we're going back to functions, and there'll be some parts that will be repetitive, like going back to the days when we first looked into functions. And we're going to carry this over to what will be regarded as inverses of functions, where we're going to have within the family of functions what will be regarded as one-to-one functions. And we have, now just going back to our old definition regarding functions. And again, a function is going to be a mathematical relation where in the xy coordinate system, and it doesn't have to be the xy coordinate system, but just with the conventional xy system. Okay, for each x value, okay, and again, that's going to be regarded as the input or independent variable. Okay, for each x value, okay, there is only one corresponding, or I should say there is one and only one corresponding y value. And again, y is going to be the output or dependent variable. Okay, and now within, again, the family of functions, okay, we have a subgroup, okay, that would be regarded as one-to-one functions. And a one-to-one function is going to be a function whose inverse is also going to be a function. And what I mean by inverse, not like in the sense of multiplicative inverse, like 3 over 4, 4 over 3. What I mean here is that inverse you have essentially where you have swapping out or interchanging the x and y variables. Okay, like if a graph had, let's say, 3, 1, and the 3, 1 belonged to a one-to-one function, well, the inverse of this would have the ordered pair 1, 3. Okay, and now some details, okay, regarding one-to-one function. Okay, now a function again satisfies the vertical line test. Okay, and now so in general, functions will satisfy the vertical line test. Okay, but what is going to make a one-to-one function distinctive from other functions is that a one-to-one function is going to satisfy both vertical and horizontal line tests. And back when we first looked into functions, I presented or started out with ordered pairs, and I'm going to do the same thing with one-to-one functions. And for what we have in the case of examples, one-to-one functions. And we'll have, first of all, let's say that we have, say, f of x is going to consist of the ordered pairs. Okay, let's say we have 1, 3, 2, 5, 3, 7, and also 4, 9. Again, just for the characteristics. Okay, now we have with the domain will be the set of the x values that will define the function. Okay, so in this case, okay, we have so you have 1, 2, 3, and 4. And for what we have in the case of the range, there's going to be the y values. Okay, so if I read in order from left to right, so I have 3, 5, 7, and 9. Now, for this function, again, we have for each x value, there is only one corresponding y value. And this is also going to be a one-to-one function, and that's because its inverse is going to be a function. And so for the inverse, the notation we will use for this one. All right, you could have it like g of x, h of x, but just to signify that we are directly taking the inverse of f of x. Okay, we have what looks like f to the negative 1 of x, and this will be your traditional inverse notation for a given function. So you have the inverse of f of x, and we have with the interchanging. Okay, so we have what was 1, 3 and f of x. We're going to have an inverse. Okay, we have 3, 1. Before we had 2, 5. Now the inverse will have 5, 2. And we had f of x with 3, 7. And so the inverse will have 7, 3. And 4, 9 was an f of x. And so the inverse will have 9 and 4. Again, for each x value, okay, we have only one corresponding y value. And for the domain, this time we have 3, 5, 7, 9. And for the range, we now have 1, 2, 3, and 4. And if you notice, we have swapping out the domain in one is going to be the set of values in the range for the other. And again, just to restate, okay, so we have 1-to-1 function. And its inverse. Will have interchanging x and y values. All right, and another case of one-to-one function. Okay, and we'll say we have for g of x. And we'll say we have among the ordered pairs. Okay, we have -1, -4. Zero, 6, and we'll say we also have 2, 13. So we have for this function, okay, we have for the domain, okay, we got -1, 0, and 2. As for what we have in the case of the range, okay, we have -4, 6, and 13. And for the inverse of g of x, okay, so we have -4, -1, followed by 6, 0, and then by 13, 2. And for the domain, again, so we're now going to have -4, 6, and 13. And for the range, okay, again, that will be -1, 0, and 2. All right, so we're looking at these items, okay, through the prism of ordered pairs. Okay, now in terms of graphs, so you have given graphs, and we have posed a question, okay, do we have a one-to-one function? let's say we have here see we have a graph. And say we have something like y is equal to, or f of x is equal to 3x plus 4. And again, in terms of graphing, okay, it's going to have to satisfy both the vertical line test first of all, so you have intersection no more than 1 point whenever the graph is intersected by a vertical line. Okay, so it is at least a function. And to be one-to-one, it must also satisfy the horizontal line test. Okay, so you had no more than 1 point of intersection Okay, and so for what we have in this particular case, now the answer to that question is yes. F of x or y is equal to 3x plus 4. Okay, that is going to be a one-to-one function. And let's say if we have something that is in the form of, let's say, and we say we have g of x is equal to the absolute value of x. Again, the absolute value of 0 is 0, absolute value of a positive is a positive, absolute value of a negative is going to be a positive. Okay, now in terms of testing out, okay, first of all, we're going to have the graph of g of x, okay, to be a function. It does satisfy the vertical line test. But for the horizontal line, it's like once we get above the x-axis or the point of origin, notice right away, okay, you're going to have intersection points. And so in this case, for the horizontal line test, okay, you have for interchanging the language, okay, for a horizontal line test, it's also going to be where for each y value, there's going to be only one corresponding x value. If you notice here, you have same y, two distinct x values. So this is no, and the reason for this is that it fails the horizontal line test portion. It is a function, but not one-to-one. And for what we have in the case of, let's say, I'm going to sketch this out as well. have something like f of x is equal to, let's say we have 3 times x to the 4th. Okay, so that will at least be a function. And again, so we have a function, but just a little bit of history to repeat. Okay, this one is not one-to-one. It fails the horizontal line test part. Okay, so that one is not one-to-one. And if I have something like this, okay, so you have a function. Let's say we have g of x is equal to the negative 2x cubed. Okay. So again, it's going to satisfy the vertical line test. And as we go up and down, moving continuously, okay, have intersection by at most 1 point between a horizontal line and the graph. So this particular function is going to be one-to-one. Okay, so if it satisfies the vertical line test, okay, it is a function. But if it satisfies both the vertical and horizontal line tests, okay, it is going to be a function that is one-to-one. All right, now, and what we have regarding one-to-one functions, okay, there is another trait regarding one-to-one functions. Okay, now a one-to-one function and its inverse. Will compose together as x. Just kind of going back to quite a few sections ago for composition between functions. You can see I have like f composed with its inverse of x. And I can do this. See, f of the inverse of f of x, and that's going to go to x. And if I do the reverse order, so I have the inverse composed with f of x. That'll be the inverse of f of x. And this will be equal to x. And way of kind of phrasing this, Okay, so you have the graphs of a one-to-one function and its inverse. Will have symmetry. With respect to the line y is equal to x. Okay, so one-to-one function and its inverse, okay, when both entities are graphed, okay, we have symmetry with respect to the line y is equal to x. All right, and now let's say that if we have a specific function, and we'll cross over into the threshold case, you have determining functions or inverses of one-to-one functions. Okay, and we'll say here, okay, say we have if we're to look for the inverse, let's say we have f of x is equal to 2x plus 6. Okay, so this is the function we are starting out with. Okay, so you have f of x is equal to 2x plus 6. Just sort of initiating. So you have f of x is equal to 2x plus 6. And what I'm going to do here is I'm going to translate the f of x and just put this, rewrite this function as y is equal to 2x plus 6. Now crossing over to the inverse threshold, I'm going to interchange x and y. In other words, what was y becomes x and vice versa. So in the interchange case, so I have x is equal to 2y plus 6. And what I'm going to do here is that I'm going to rewrite this in terms of y equals. And it's not going to be y is equal to 2x plus 6. It's going to be something entirely different. Okay, so right now I have x equal to 2y plus 6. And if I get the y term by itself, okay, so I'm going to take 6 away from both sides of the equation. So we're going to have x minus 6 is equal to 2y. And we have dividing by 2. So you have x minus 6 over 2 is equal to y. And what I can do here is I can just have the y term on the left hand side, so kind of taking the commutative property of equality, like going from b is equal to a is equal to b. So you have y is equal to x minus 6 all over 2. And okay, and so for this y, if I put it in functional notation, now on the basis that we had the first y to be spun off, okay, from f of x, that particular y is going to be in reference to the inverse of f of x. Okay, so you have the inverse of f of x. Okay, so that is going to be x minus 6 over 2. And just finally declaring so in this case, we're going to have the inverse, okay, again, to be at x minus 6 all over 2. And again, these functions will have interchanging x and y values. And just see if I can squeeze in a visual on this one. Okay, so we got, in this case, you have for the function so f of x is equal to 2x plus 6, and we just call it the inverse. Desmos does seem to pick up on the inverse notation, but for this one, okay, we have for the inverse, okay, so we got x minus 6 all over 2. Again, we have y is equal to x. And if I add in just a few details, okay, so you got, I'm going to do here, okay, now again, a one-to-one function and its inverse will have interchanging x and y values. So where we had -8, -10 before, we're going to have -10, -8, and then we have -6, -6, -2, -4, and let's see, and we'll have 2, -2, and also 6, 0. And again, we're going to have the graphs to have symmetry about the line y is equal to x. And if you notice, okay, all three of these come together where we have -6 and -6. Okay, so in this particular case, right, so this is a case of one-to-one function and its inverse. Okay, and so again, a one-to-one function and its inverse will have interchanging x and y terms, and will have symmetry about the line y is equal to x. Okay, now, and let's say that if we have another scenario, and we'll say that we have a function g of x, and we'll say that for this one, okay, we'll say that g of x is going to be equal to 1/3 of x minus 4. Right, so just getting things set up here. Okay, so g of x, okay, we have 1/3 of x minus 4. Okay, so again, I'm going to do a bit of a change up. Okay, so I got the explicit functional notation. Then I'm going to go over to the implicit where I'm going to write g of x is y. So I have y is equal to 1/3 of x minus 4. And then crossing over to the inverse, once again, I'm going to interchange x and y. So we have here, okay, so we have x is equal to 1/3 of y minus 4. And I'm going to isolate, okay, the y term. Or I can multiply the equation by 3. We'll go that route. Since I'm looking at solving for y, okay, so we have 3x is equal to y minus 12. And I can now isolate y. Upon adding 12 to both sides. And we have that 3x plus 12 is equal to y. And if I switch the order to have y on the left-hand side, so I have that y is equal to 3x plus 12. And again, just for this y, again, looking at the inverse, now my original function was in the form of g of x, and we'll just take the inverse notation. So I have the inverse of g of x is equal to 3x plus 12 to just formally addressing. Okay, so we have the inverse. Okay, we have to be the inverse of g of x. Okay, and so that is going to be equal to, once again, 3x plus 12. All right, and just again taking a visual. So 1/3 of x minus 4. Again, the inverse, we'll just call this h of x. So yeah, 3x plus 12. And again, we have the line, okay, y is equal to x. I think I'll change the color on this one. I'm throwing some ordered pairs here, so you have -9, and let's say the next one will be -6, -3, so you have 0 and 3. Okay. And for the inverse, okay, so if I take this order pair from g of x and swap out or interchange the x and the y, so I have -7, -9, -6, -6, -5, -3, -4, 0, and we're going to have -3, 3. And again, we're going to have symmetry with respect to the line y is equal to x. Okay, so 1-to-1 function and its inverse. Again, we'll have symmetry with respect to the line y is equal to x. Okay, let's see. Yeah. All right, and now in looking at what we have in the mix, okay, let's say that in looking for inverses, we'll say that for our functions. Let's see. Say just for the next few minutes. Okay, let's see what we get for the inverse of h of x is equal to 2x minus 8. Then after that, let's see what we get for m of x is equal to x minus 7 all over 3. In other words, like 1/3 of x minus 7/3. Okay, so let's see what we get for the inverses of these particular functions. Okay, if you're still working on these, that's fine. Now, looking for the inverse of these functions, okay, so we have, first of all, okay, so we have for h of x is equal to 2x minus 8. Okay, so again, h of x, okay, this is going to be a functional notation for what we say is y. Okay, so h of x equals 2x minus 8. Again, this translates to y is equal to 2x minus 8, and then crossing over into the threshold of the inverse territory, we will have once again the interchanging of x and y. And so we will have here that x is equal to 2y minus 8. And looking at solving for y after the interchange, so we have the y term at 2y, and if I isolate upon adding 8 to both sides, so I have that x plus 8 is equal to 2y, and then we have with division by 2. Okay, I can just swap the order. Okay, so I have that y is equal to x plus 8 all over 2. And just putting, once again, in terms of inverse notation. Okay, so I start out with h of x and the inverse. Okay, again, we say that the inverse of h of x is equal to x plus 8 over 2. And this can be expressed in another fashion. Okay, so we're going to have for the inverse. Okay, so I have the inverse of h of x. Now it's a consolidated statement. Okay, we have x plus 8 all over 2. And again, if I were to itemize, you can also say that we have 1/2 of x plus 4. Two different ways of saying the exact same thing. And so just looking at what we have in our setup. Okay, so we got in the layout. Okay, so just kind of taking what we have here. So I have h of x equal to 2x minus 8. Now I'll just call the inverse, or just let this be, say, k of x. And do it this way. So you have x plus 8. All divided by 2. And we have, in terms of the graph here, you have symmetry with respect to y is equal to x. Okay, so again, just sort of stressing what we have. So we'll just say we have okay, say for the function h of x is equal to 2x minus 8 among the order pairs. Okay, you have 2, negative 4, 4, 0, 6, 4, 8, 8, and 10, 12. And if we swap, okay, we're going to have to consist of the ordered pairs and inverse. So say we have, in this case, we have negative 12. Let's see. Oh, no, it did here. Take 2. Okay, so you have negative 12, negative 2, negative 10, negative 1, negative 8, 0, negative 6, 1, and negative 4, 2. And if I were to, let's say, venture out further, so let me change these order pairs. Then this will show it better. 2, negative 4. Yeah, that's more like what I want. Yeah, so for these items, okay, so again we have interchanging x and y values. Okay, yeah, get a little bit of crowding effect here. So we'll just zoom in. There we go. And if you notice, you have symmetry with respect to the line y is equal to x. Okay, so you're going to have your x and y values to be the same for both functions whenever x and y happen to be meeting, okay, where the twain shall meet, okay, where we have the values end up at 8. All right, now for what we have in the case of the second function, okay, so we have in this one, okay, now we've got m over x is equal to x minus 7 all over 3, okay, and just kind of taking what we have and again, just like h of x, m of x, okay, is a functional notation for what we say is y. So you have y is equal to x minus 7 all over 3. And if I interchange x and y, so you have that x is equal to y minus 7 all over 3. And if I just go ahead and multiply the equation by 3, so we're going to have in the rewrite, we'll have that 3x is equal to y minus 7 and getting the y term by itself. Okay, so if I add 7 to both sides, oops, 3x plus 7. So 3x plus 7 is equal to y, and just swapping the order, okay, so I have that y is equal to 3x plus 7. Now for the inverse, we started out with m of x. Now the inverse notation, we have the inverse of m of x is equal to 3x plus 7. Okay. And so this is how all of this is going to end up playing out. And now, for what we have in the case of this function, again, the graphs will have symmetry with respect to the line y is equal to x. Okay. And just kind of reestablishing, okay, so 1 to 1, and its inverse will have interchanging x and y values. So you have -5, -4, -4, -5. So got -2 and -3 just swap out. -2 and 1 we'll do likewise. As well, -1 and 4, and also we have at 0 and 7. Okay. Okay, so I have interchanging x and y values. And let's see now the point at which they're going to meet. Okay, we'll have non-decimal values. Okay, so where all the graphs will come together and intersect along with y is equal to x. We have x and y to both be at -7/2 or -3.5. Okay, now so far we have dealt with the one-to-one functions where they have been linear functions so far. And let me mention something regarding it's going back to domains and ranges. Okay, now again we have dealt with one-to-one functions so far where they have been on display as linear functions. And I'm just going to mention this in case. So just going to put stress. I'm going to stress this. Okay, all domains and ranges of linear one-to-one functions and their inverses will be all real numbers. Or once again, just utilizing interval notation. So you have between negative and positive infinity. Okay, so but for that, again, to automatically be a guarantee, the one-to-one function has to be one that is linear. Okay, where the independent variable has to be no more than, or it has to be first order. Okay, and for what we have, let's say if you have something that is kind of a one-to-one function, but it's going to have to be, we should say, sort of adjusted. Okay, let's say if you have say if you have a function that is nonlinear. If I'm looking for the domain and the range, and so we have f of x is equal to the square root of x plus 4 followed by the subtraction of 3. Okay. Alright, so you have f of x equal to the square root of x plus 4 minus 3. Okay, so you have, you know, so you're going to have some restrictions placed. Okay, first of all, we have with the square root radical. This is going to signal that x plus 4 cannot be negative. So we're going to have that x plus 4. Now, because this is given in direct terms, you know, x plus 4 can be 0. It can be positive, but it cannot be negative. Okay, so x plus 4 is greater than or equal to 0. And so we're going to have that x is going to be greater than or equal to negative 4. So this is going to signal, at least for the domain portion, okay, so you have for x is greater than or equal to 4. Okay, now the set builder notation, we have that x is greater than or equal to negative 4, or the set of all values of x such that x is greater than or equal to negative 4. But again, if you use the interval notation, so we have going from and including negative 4, we have approaching infinity. All right, and so just so we got the domain part. Okay, now if we step back and look for the range. Okay, so and just some items here. So just going back. So you have f of x equal to the square root of x plus 4 minus 3. Now in terms of the range, okay, now we have f of x, okay, we have, again, that's the functional notation for what we say is going to be y. Okay, and we're looking at what we have to be in the range of this particular set. Now again, domain is in reference to x, range will be what we have regarding y. Okay, and let me mention here now for the square root of x plus 4. Remember, the square root of a value cannot be negative, and it can be 0. Okay, and so the smallest possible value the square root of x plus 4 is going to be 0. And so for what this is going to imply, okay, is that the smallest possible y is going to be equal to, okay, since the square root of x minus, I should say the square root of x plus 4 is going to have its minimum possible value to be at 0. Okay, so we have y is equal to, in essence, okay, we have 0, and then we have minus 3. Is equal to negative 3. So the smallest possible y value is going to be negative 3. All other values in y will be greater than. And so for what this is going to signal, okay, is that for the range, okay, so you're looking at, I'm just going to present the set builder notation once again. So you have a set of all values of y such that y is greater than or equal to negative 3. And for the interval notation for values in y, okay, so we're looking at going from and including negative 3 on out to infinity. So for the domain, for what we have in x, will be those values from and including negative 4, and then increasing continuously, whereas in the case of the range, we're going from and including negative 3, and then we have a continuous increase from then on. Okay, and now let's say that, just referencing this function once more. Okay, so if I have to determine the inverse of f of x, okay, we have is equal to the square root of x plus 4 minus 3. Okay, so just starting out, okay, so you have f of x equal to the square root of x plus 4 followed by the subtraction of 3, and just writing f of x as y. Okay, so I have y is equal to the square root of x plus 4 minus 3, and then just crossing over to the inverse stage. So if I interchange x and y, okay, so I'm going to have that x is equal to the square root of y plus 4 minus 3. And if I isolate the y term, so I'm going to get the square root of y plus 4 by itself. So I'm going to add 3 to both sides. So I'm going to have the x plus 3 is equal to the square root of y plus 4. Okay, and then to free up the y expression from the square root, okay, so I'm going to square both sides. And for the square of x plus 3, this will be x plus 3 times itself. So we have x squared plus 6x plus 9 is equal to y plus 4. And if I get y by itself, okay, so I'm just going to take 4 away from both sides here. So we have x squared plus 6x plus 5 is equal to y. So you have that y is equal to x squared plus 6x plus 5, and it's going to follow that if I put in inverse terms, so you have the inverse of f of x is equal to x squared plus 6x plus 5. So that will be your inverse function. But I want to mention something about domains and ranges. So you have f of x. Okay, again, that was the square root of x plus 4 followed by the subtraction of 3. And again, we had for the domain of that function, okay, had from -4 to infinity for what we had in x. And the range for what we had in y. Okay, so you have from and including -3 on out to infinity. Now for the inverse function, again, we're going to have interchanging x and y values. Okay, so we have the inverse function again, that was x squared plus 6x plus 5. Now for the domain, again, your x and y values will be interchanging. Now where we had the range in the original function to be from x equals -3 on out to infinity, or say y is equal to -3 on out to infinity, that's going to translate to the same thing for x in the inverse. And guess what? For what I had in x for the original function, I'm going to have in y in the inverse. Okay, so those are going to interchange. And I'm just going to go ahead and squeeze this in just to kind of illustrate something that we have. Okay, just a kind of an added dimension to be looking into. So we have, again, so we have f of x is equal to the square root of x plus 4 minus 3. Okay, so you have a square root function. And okay, now for the inverse, I'll just call this g of x is equal to x squared plus 6x plus 5. We got y is equal to x, and then we just modified this a bit. Yeah, and if you notice, okay, that doesn't look like symmetry throughout because there's too much in the parabola. But notice, okay, from before I had the restriction for the inverse, okay, that the values of x have to be greater than or equal to -3. So if I adjust voila, you're going to have symmetry throughout. Okay, and so these portions will reflect each other or mirror each other about the line. Y is equal to x, and they happen to intersect at like -1.382